So to begin with, kind of a concept, what do you think of soil? Usually when people think of soil, they think brown dirt. And I want to stress that it's a lot more than that. But going back to the very basics, sort of a conceptual idea. This isn't so much of a scientific idea, it's more of a conceptual idea. You can think of soil as being both the skin of the earth, but also the intersection of the three spheres of matter. So if we break down all matter into three spheres, we've got the hydrosphere, which is all of our water. That would be from the largest bodies of water like the oceans to tiny little droplets of water vapor up in our clouds, to groundwater, to small streams, to large streams, to rivers, to lakes, all the bodies of water in any form, whether it's gas, liquid, ice, that would be your hydrosphere. Your lithosphere is rock and pulverized rock. Basically, no matter where you are in the world, if you dig down deep enough, you will eventually hit bedrock. And all that solid rock breaks down into smaller pieces, powdery rock and dust as well too. That's your lithosphere. And then lastly, there's the atmosphere, which is pretty self-explanatory, the air above us, where all three of those spheres come together and mix right at the surface of the earth, the skin of the earth. That's where we get soil. So that's an interesting concept because we think of soil as a solid, but you really have to appreciate the important role that air and water also plays in soil as well too, in addition to that solid rock, the lithosphere. And we can see this when we look at a pie chart of what soil actually is. It really is a combo of air, water, and gas. So a healthy topsoil, and I should say healthy, and we don't all have healthy topsoil, but we have a nice healthy topsoil. What we should see is a material that's only half solid. So 50% solid, and the rest is pretty much evenly divided between gas, what we call the soil's atmosphere, which is different from the atmosphere above ground, and water. So 50% solid, 25% by volume gas, 25% by volume water, which is generally a lot more gas and water than people think when they think of soil. Now, if we get even a little bit more specific, we can break down those solids into some subcategories. About 5% of our soil is organic matter, and the other 45% of the soil solids is mineral matter. Okay. So even though solids are only 50% of the volume of soil, they're still very important because generally when we're talking about soil, when we're describing the differences from soil from one spot to another, we're usually talking about changes in the soil solids. So even though there's not as much of them as we might think, they're still very important. So again, 45% of our soil is the mineral fraction. What does that really mean? Sand, silt, and clay. That's what our mineral fraction is, little pieces of sand, silt, and clay. So about 45% of the volume of your soil will consist of sand, silt, and clay. The other 5% of that half that is solid is organic. And the organic fraction of the soil solids consists of both living organisms and dead decomposing organisms. So alive stuff and dead dying stuff. Even though it's only 5%, it's a very important fraction of the soil. What is sand, silt, and clay? Well, there's lots of different types of sand, there's lots of different types of silt, there's lots of different types of clay, and those differences come down to the mineral content, what atoms or minerals or elements they're made up of. We're not going to get into that because that can get very complicated very quick. What we're going to look at today is just generally, what is the difference between all sands, all silts, and all clays? And it is strictly a difference based upon size. So sands are bigger than silts, which are bigger than clays. They're all mineral particles, and there's a variety of mineral particles that can create a sand, a silt, or a clay. But if we're just talking about the differences between those three categories, we're talking about differences in size. So these are kind of unusual sizes. Sand is any mineral, and this is going by the Department of Agriculture, the US Department of Agriculture. They consider any mineral particle with a diameter between 2 and 0.05 millimeters to be sand. Any mineral particle with a diameter between 0.05 and 0.002 millimeters is silt, and anything less than 0.002 millimeters in diameter is a particle of mineral clay. 0.002, that's kind of an odd number. What does that really mean? That means 2 microns, 2 millionths of a meter. So clay is really, really, really small stuff. You'd need an electron microscope in order to see individual particles of clay. Silt is microscopic as well too. You need a less powerful microscope to see those individual particles of silt. And then there's finally sand, which kind of crosses the border between visible and microscopic. A 2 millimeter size particle of sand, you can see that with your eye. You get down to 0.05 millimeters, yeah, we're getting kind of verging onto the microscopic territories there. What you really should take from this is sand is a whole lot bigger than silt, and a particle of silt is a whole lot bigger than clay. And the picture shown there is a pretty good approximation of the relative sizes of sand, silt, and clay. So sand, silt, and clay, the mineral fraction of soil is 45% of your soil volume. 5% of your soil volume is your organic fraction, and this consists of living material. So anything alive in the soil, we actually consider to be part of the soil, whether it's something very familiar like your earthworm, or smaller stuff like these microscopic or barely visible small insects like springtails and mites, down to the really microscopic stuff, individual cells of bacteria, and microscopic soil fungi. Fungi can be both macroscopic. Have you ever seen fungi growing on the side of a dead log in the forest? That's macroscopic fungi that you can see, but most soil fungi is microscopic. They exist as these little tiny thin root hairs that just stretch out through the soil. And then there's the dead material as well too. So the leaves that fall down in the autumn and land on the soil surface and start to decompose and get crunchy. Those all begin to break down. That dead and decomposing organic material eventually breaks down into what we call soil humus. Soil humus is sort of like the resistant organic material that is left after all the easy to decompose organic material has been broken down into carbon dioxide or been incorporated into the bodies of microbes or other decomposers. It's this nice dark material. Basically, if you have a compost pile, what you're creating is humus. When you're looking at topsoil and you see a nice dark topsoil layer at the very surface of your soil, what you're looking at is staining caused by soil humus. So there's a lot of overlap between the living material and the dead material in a soil because it's the living material, especially those microbes, the bacteria and the fungi, that snack on that dead material. That dead material, those dead leaves, twigs, dead animals, manures, those are the food source for that living material. That living material relies on that dead material as its energy source, as its food source, and in the process, they break down and decompose that dead material and create soil humus, which is a very important ingredient in healthy soil. So even though it's only 5% of the soil, both the living material and dead material combined, it's a very important part because through this process of the living microbes in soil breaking down the dead material and decomposing it, it releases nutrients out into the soil. And this is how nutrients are recycled through the soil and really through the entire world. So this process of breaking down organics is a really important process in the health of soil and the health for all of us. And again, 5% of the soil is living and dead material, this organic fraction, but the numbers are still huge. If you look at a teaspoon of topsoil, healthy topsoil, every teaspoon will have about 100 million to 1 billion bacteria living inside. And you'll also have, for those fungi, those little tiny fungi roots, we call them hyphae, those little tiny microscopic roots. If we were able to extract those roots from that teaspoon of healthy topsoil and lay those fungal roots end to end to end, they would stretch anywhere from 40 yards to 40 miles per teaspoon. So there's a tremendous amount of living organic material, living critters in the soil. Most of it, though, we can't see because it's microscopic. So a quick recap. What is soil? Conceptually, I like to think of it as the skin of the earth, where the hydrosphere, the lithosphere, and the atmosphere all mix together. It's 50% solid material by volume, 25% air, and 25% water. And those solids are composed of mineral material, sand, silt, and clay, and the living and dead organic material. And you need one final thing for it to be considered soil. It has to be able to support life. So, sometimes you'll hear stories about lunar soil, soil on the moon, or the Martian soil, soil on Mars. Well, technically, from a soil scientist perspective, we wouldn't consider that to be soil because it's not able to support life. So that's kind of a minor thing for our purposes, but an interesting point nonetheless. How does soil form? It's a slow process of weathering and the transportation of rocks, sediments, and organics by natural processes. So you can imagine a big chunk of granite bedrock. sitting out there on the soil surface. That's going to take a long time to break down into those little 2 millimeter or less particles of sand, silt, and clay. So that process, breaking down that solid rock could take thousands, potentially even up to millions of years to break solid rock into sand, silt, and clay. Organics break down a little bit faster. If you have a compost pile, throw a banana peel on there, you come back the next day, you see that banana peel is already beginning to degrade pretty well. It's probably getting brown, it's probably beginning to break apart. So it can take from days to decades to break down organic material. Soil humus, sort of the resistant stuff that is resulting when all the other organic matter breaks down and is decomposed. Soil humus can actually stay in the soil for 100, 150 years, slowly decomposing that entire time. So it's a little tougher than we think. But between those two processes combined, breaking down those solid rock and breaking down the organics, it's estimated that it takes anywhere from 100 to 500 years to create every inch of soil. So is soil a renewable resource? Yes, but it's very, very slowly renewable. And if we degrade soil now, we probably won't be able to fully get back its health until several generations down the road. Now, I mentioned at the beginning that a lot of people, when they think of soil, they think of brown dirt. Well, it's not that. It's much more variable than that as well, too. There's a lot of variation in soil colors, in the depths of soil. Some soil is very shallow. Some soil you can dig for 20, 30, or 40 feet. The chemical makeup and nutrient content of soil, is it fertile? Does it have a lot of nitrogen, phosphorus, and potassium and other stuff that plants needs, or does it not have that stuff? That's very variable from spot to spot. The age of the soil, you go to a floodplain, you're looking at pretty new soil, probably stuff that was deposited in the last flood. You go to the top of a hill, that soil may have been sitting and forming in place for 30 or 40,000 years. The wetness, how deep do you have to go in order to hit groundwater or saturation? That varies from spot to spot greatly. And the acidity, some soil is naturally very acid, some's fairly basic, and some's right there in the middle and neutral. And all these things combined create a lot of variability from soil, not just in big landscapes like across the United States, but in local landscapes as well too. I work in Fairfax County, and just to give you an example, Fairfax County is not that big in terms of its landmass, but it has 110 different soil types recognized just in the county. So there's a lot of variability from soil, even in smaller areas. So the point of this is soil is not just plain brown dirt. It can look different, it can be different, it can have different health and a lot of different characteristics. How does this variability come about? Well, there are sort of 5 natural factors, 5 natural forces that combine together to create different soils from spot to spot. And the way these factors influence and interact with the land creates that variability of soils. We call these the 5 soil forming factors, and they have a really bad acronym. However, it's so bad that I think it makes it memorable. So hopefully by being so bad, you'll remember it, because undoubtedly somewhere along the line in the competition, you're going to see a question about the 5 soil forming factors. So here's their terrible acronym. It's CLORPT, C-L-O-R-P-T. Sounds to me sort of like you toss a pebble into the middle of a pond and it makes that sound when it splashes down, CLORPT. If you can remember CLORPT, hopefully you will remember the 5 soil forming factors. So what do they stand for? Well, the CL in CLORPT stands for climate. O stands for organisms, not organics. A lot of people confuse that, but organisms. R stands for relief. Relief is just a fancy word for where are you in the landscape position? Are you up at the top of the hill, down at the bottom? Are you on a steep slope? Are you on a flat plain? So R is relief or landscape position. P is the parent material, the material from which the soil formed or weathered. And T is time. Climate, organisms, relief, parent material, time. Those are your 5 soil forming factors. What makes up these factors? Well, when we're talking about climate, really it's rainfall and temperature. And the general rule is the hotter and wetter the climate is, the faster material decomposes and breaks down, both rock and organic material. Organisms. They play a lot of roles, but one of the most important roles they play in soil formation is the breakdown and decomposition of organic matter. R, relief. Where you are in the landscape really affects the amount of erosion and the type of drainage you have in your soil. If you're up at the very, very top of the hill, chances are you have a really dry soil. If you're down next to a creek or in a low valley, chances are you're probably going to have a pretty wet soil. Water goes in one direction, downhill. Erosion is sort of the same thing. If you're on a really flat summit, you probably don't have a lot of erosion. When water falls onto that flat summit, most of it will just soak down into the soil. When you're on a really steep slope, however, when you have that same rainfall, a bunch of the water that falls on that steep slope is going to become surface runoff, and it's going to wash away some of those fine sand, silts, and clays up on the surface. So that soil will probably be a little bit more eroded. So the relief has a big effect on the erosion and the drainage class of the soil. Parent material. So just like we get traits from our parents, soil gets traits from its parent material. And the material from which the soil forms, the rock from which it weathers, the sediment from which it weathers, really has an important effect on chemistry. Basically, is it acid? Is it basic? The color, the texture. The texture is the percentage of sand, silt, and clay. There are certain rocks that when they break down and form soil, they form really, really, really sticky clay soils. There's other rocks that will break down just kind of physically. They break down into smaller pieces of rock, and eventually they form sort of very gritty, sandy soils because the chemistry of that rock is very tough to break down. It's a very resistant material, and all you can do is really pulverize it into smaller pieces of rock. Those types of soils generally tend to be kind of gravelly and sandy and gritty. And then lastly, there's time, which is sort of your master variable. Climate, organisms, relief, and parent material all need a lot of time to interact and work on those big solid pieces of bedrock or that unweathered sediment and break it down into the soil that we recognize today. So again, remember, it's about 100 to 500 years to create every inch of soil. So if our soils around here are anywhere from about 3 to 5 feet deep, that probably means that those soils have been forming and weathering in place for 10, 20, 30, 40,000 years. So soil is pretty old. When we're looking at CLORPT and the change in soil types, the variety, at the regional scale, meaning the big scale, why is our soil here different from our soil in California, different from our soil in Florida? Really, that's climate. Climate makes those big changes over big areas. So California and Florida have very different climates than us, and they have very different soils than we have as well, too. It's not the only thing making those changes in soil, but it's one of the big ones. On the local scale, let's say, why is the soil where I'm sitting at the top of the hill different from the soil down at the bottom of the hill? Or why is the soil at my house different from the soil at my neighbor's house on the other side of the street? That's usually more an issue of relief, so the landscape position, and the parent material, what type of rock or sediment that soil weathered from. Those can really make the differences in soil over small areas. And of course, this is a generalization. There are exceptions to this. To use, again, Fairfax County as an example, we're not a very big county, but we do have different parent material types from spot to spot. Sometimes the difference in soil is not so much a result of the relief, but really that the soil across the street has a different rock type. Again, there are differences, but that's a fairly good general rule. Climate makes big changes over big areas. Relief and parent material make big changes over small areas. Meredith, this might be a good time to answer any questions that have come in, although I don't think I've seen any.
Yeah, I don't see any popping into the chat, but if anyone wants to go ahead, we can give a minute or two for people to put things in the chat or to raise your hand under participants and then raise hand. And that way you can unmute yourself and speak your own question if you'd like to ask Dan directly.
I think I'll go through this slide, and if anybody raises their hand, we'll get to it after I finish the slide. Just so
Sounds
we can
good.
keep clicking along. Oops. So soil formation and action. So we've got the 5 soil forming factors. Those are sort of the forces that are driving this whole process of soil formation. But what are the actual mechanisms? How do these 5 soil forming factors physically interact with the ground? Well, we've got these sort of 5 processes that happen. There's inputs, there's translocations, transformations, and losses. This is a fancy way of saying things get put into the soil, things are washed out of the soil, and while they're in the soil, they move around and they change form. What are the inputs? Well, the big inputs are organic matter. As plants grow on the soil surface, they add organic matter through leaf fall, through dropping sticks and twigs, but also they actually pump organic matter into the soil through their roots. So carbon is associated with that organic matter. So a lot of carbon is pumped into the soil as a result. In addition, you do get carbon dioxide, dissolved carbon dioxide coming in with the rainfall. Rainfall is another input itself. Snow, ice as well too. And then lastly, oxygen. Oxygen diffuses from the atmosphere and passes down into the soil. So those are the four big inputs. And as things are added to the soil, they move around into the soil as well too. And one of the big processes, or what we call a translocation, is that clay generally tends to form up in our topsoils, but over time, as the soil ages and weathers in place, that clay is driven down deeper into the soil. So generally, when you're digging in your soil, you dig through the topsoil and you get to the subsoil, and that's where you start seeing the really sticky clay parts of the soil, even though the clay actually formed up here in the topsoil. Over time, that clay layer gets thicker and thicker and thicker because every time it rains, water passes through the soil pores. It can pick up a few of those clay particles and wash them deeper down into the soil. And over time, hundreds and hundreds of years, that clay begins to build up or translocate down to the subsoil. We have transformations. Deeper down in the soil, we have parent material that is weathering and breaking down and forming the sand, silt, and clay that creates our soils. And again, that's a very slow process. And then eventually we have some losses as water continues to pass down through the soil. Soluble nutrients, nutrients that can dissolve easily, especially things like nitrogen or nitrate, will often wash out of the soil, down into the groundwater, down into fissures or cracks into the bedrock, and off into our streams and our rivers. So these are just examples of inputs, translocations, transformations, and losses. Those are the four big processes that are driving the system. And there's other specific examples we could use, but those are some common ones. And as soil forming factors and those processes we just talked about interact with the soil, eventually over time, we get this nice layered soil forming. If you were to look at soil in the field, you'll see it is a layered system. It kind of looks like a layer cake. I chose this photo because it shows the layers very well. When you're digging in the soil or you have a soil pit at one of the competitions, the layers probably will not be quite this distinct, but it shows up well on a slide, so I'm using it. But just remember, it's going to be a little more subtle to see the layer changes out in the field. What are the layers that we find? Well, as we start from the surface, we dig down below the surface. The first thing we hit is our A horizon. That's our first subsurface layer of soil. It's basically our topsoil. When people are saying topsoil, what they mean is A horizon. When people say A horizon, what they mean is topsoil. It's organic matter rich. It's usually got a nice dark brown or black color because it has a lot of soil humus in it. It's got that organic matter because it's right there at the surface. The A horizon is where the bulk of your fine roots live. It's where the bulk of your microbes, bacteria, fungi, and other critters live. So there's a lot of life going on in the A horizon, and there's a lot of organic matter being deposited and being decomposed and turned into humus in the A horizon, which is why it has that nice dark color. Now, for Virginia, we generally have very thin A horizons. You'd be lucky to get 2 to 5 inches. I'd say on average, our A horizon is only about 2 to 3 inches deep. So remember that when you're looking through your soil and you're trying to find that color change where the soil turns from that dark A horizon to the lighter submaterial, you're probably going to be looking in the top 2 or 3 inches. If you think you found it down at 16, 17, 18 inches, that's probably a mistake. Look up at the top. Below the A horizon, we sometimes, not always, I'd say about 50% of the time, find an E horizon. E to me stands for exit. It's a leached layer, meaning things have washed out of it. So everything that could give it color has washed out. If you take a nice brand new bright red t-shirt and you throw it into the wash at the highest possible temperature, what happens? The color bleeds out. That's sort of what's happening to the E horizon. As soil forms, a lot of natural acids build up. And those acids leach through, pass through the E horizon. They kind of strip everything out that can give that soil layer color. So what you're left behind is kind of this pale, washed out color. It's lighter, much lighter and paler than the A horizon above, and then the B horizon down below as well. Again, you only find it, I'd say maybe 40 to 50% of the time you'll find an E horizon in your soil. So if you don't see it, don't worry. It probably just means it's not there. But if you do see it, you're going to be looking for that leached, pale, kind of washed out color. It too is pretty thin. An E horizon, if you find one, is usually going to be anywhere from 2 to 4 inches thick, just like your A horizon. So if you find it, it's going to be up towards the top of the soil, right below the A horizon. Now, we go down to the B horizon. This is sort of our colorful layer, our most colorful layer. This is where you find the reds, yellows, and oranges that are typical of subsoils around here, because the B horizon is where you find a lot of clay. The clay forms up in the A horizon, but then it gets driven down to the B horizon as water passes through, picks up that clay and deposits it deeper in the soil. So if you find the soil is getting red, yellow, or orange clayey colors, if it's getting thicker and denser as you dig through it, if it's getting a little bit more moisture, because clay holds onto a lot of moisture, you're probably in your B horizon. And we can get really thick B horizons in Virginia. If you have a B horizon that's 12 or 18 inches thick, that's not too surprising. So below the B horizon, we get into the C horizon. This is a tough one to determine if you're in there. It's sort of a border layer. It's not quite soil, it's not quite rock, it's somewhere in between. Basically, it's parent material or bedrock that's just begun to decompose, to sort of physically pulverize. To give an example, if let's say you had a, again, that big chunk of granite bedrock, a big granite boulder. If you were to take a rock hammer and just start chiseling away at that boulder over a period of years, the pile of dust and debris that you find at your feet down at the bottom of the boulder that you've chipped off, that's kind of like the C horizon. So how do you know you're getting from the B to the C? Well, generally you start seeing the soil get drier because it's losing its clay content as you go down to the C horizon. C is usually a little more rich in sand and gravels. So it doesn't hold water very well. It gets drier. It usually gets looser and oftentimes grittier. If you see a lot of gravels or sand pick up in the C horizon, or pick up in the soil, that's a good indicator that you're in the C horizon. But really what I look for is that loss of clay. If the soil feels looser, lighter, drier, and grittier, chances are you're moving from the B to the C. The tricky part is there's often very little or a very subtle color change between the B and C horizon. They can often have very, very similar colors. So you can't always use color as a good indicator. Sometimes you can, sometimes you can't. The last horizon is the R horizon. As the name might imply, R stands for rock. So if you start hitting really solid stuff down at the bottom of the soil pit, chances are you're in the R horizon. Sometimes you can chip away a little bit of it with a chisel or at the end of a shovel, but generally if it's solid rock and you can't dig any deeper, you're in the R horizon.
And Dan, we do have a question.
Okay.
Would it be appropriate to say that the E layer is the B layer that has been leached?
It could be. It probably was at one point, because so much of the clay starts forming up in the A horizon. When the soil is very young, we might see that clay begin to accumulate in the E horizon instead. So it's sort of like the old B, but over time, that material starts moving down further and further, and this layer leaches out. So yes, it's almost like the B horizon probably was here, but then it sort of passed by and now is deeper, and everything is leaching out of here and going down into the B horizon. So yeah, I think conceptually that's probably an accurate thing to say. Any other questions?
No, I think we're looking good right now.
Okay, keeping on moving. So I should have mentioned this a little bit more before, but I mentioned in passing what soil texture was. That's the percentage of sand, silt, and clay. There's another really important physical characteristic of soil called the soil structure. And the soil structure is how the soil solids clump together, how they are arranged together. Again, when we think of soil, we think of a solid, but if we really look at it, it's almost like a bowl of cereal. If you look very closely at soil, it consists of these little individual clumps or aggregates that we call PEDs. And between those PEDs, and even inside of the PEDs, there are pore spaces. And those pore spaces between the PEDs are what allow for soil to have only 50% solid material and also 25% air, 25% water. It's those open pore spaces that allow all that volume of air and water to get into the soil. So it's very important that soil has good structure, meaning that it does clump together and it's got fairly good sized pores between each of these little clumps or PEDs, because that's how oxygen, water, and nutrients get down into the soil, into the roots, and to the microbes that break down organic matter. So if we were to pry out some of the PEDs, the clumps in soil, they might look a little something like this. Usually up in the topsoil, we have what we call granular structure, and they look like these little grains. They kind of look like grape nuts, both in terms of their size and their shape. If anybody's had grape nut cereal, the texture, the granular texture common in A horizons is very similar to grape nuts. As we get down deeper into our B horizon, where we have more of that clay, we have this blocky structure, letters C and D up here. And blocky structure looks a lot like granular structure, it's just bigger. A and B, these are columnar and prismatic. You'll find that every now and then in really clay soils, but we don't have a lot of that in Virginia. I'll mention it, but I don't think you'll see it. What we do have a lot of is this platy structure. And this can be naturally formed, but a lot of times this is the result of humans, of us, compacting the soil. When we put a heavy weight on top of the soil, we run over it with a car or with construction equipment, or we build a building, we take this nice, loose, granular or blocky structure and we squish it, and we create these flat plates that are tightly interlocked. And this, unfortunately, is a type of structure that doesn't allow a lot of air and water down into the soil, because all the pore spaces, not all, but a lot of the pore spaces have been squished out or greatly reduced in size. So this platy structure here is often a sign of soil compaction, both either on the farm or in cities and suburbs. How do you create soil structure? How do you get those individual particles of sand, silt, and clay to clump together like that? Well, you need a binding agent, something to glue stuff together, to cause that aggregation. And some good binding agents in soil are both clay and organic matter, especially humus. They're naturally sticky, so they tend to clump together. Microbial decomposition is a great source of binding. As microbes, bacteria, and fungi break down organic matter, they create a lot of byproducts that have sort of a naturally gluey kind of texture to them. And those tend to cause sand, silt, and clay particles and other organic matter particles to clump together. And then you have those fine root hairs, those little tiny roots, hyphae of soil fungus. They tend to act like thread that sort of binds things together. And even some of the fine plant roots, which are bigger, can bind these little clumps together, kind of tie them up together like twine. So all those things combined tend to cause aggregation or soil PEDs or clumps to form. Now, if we just had these natural glues, we'd have one big block of soil, but we also need stuff to sort of break up the soil to create those pores. So we need burrowing agents as well, too, to create the pores between the PEDs. Worms are probably one of the most obvious and most well-known of those burrowing agents. They are basically just eating their way through the soil, making new roots all the time. Excuse me, making new pores all the time. Roots are great burrowing agents as well, too. Roots are constantly in the process of growing and dying. And when a small root dies and decomposes, its root channel becomes a nice open pore space. There are plenty of other burrowing organisms as well, too, in addition to the worms. Beetles, even bigger stuff like foxes or groundhogs, all of those are creating burrows. And then there's the strictly physical processes, wetting and drying. As soil wets, it swells up a little bit. As it dries, it shrinks. Certain clays really, really swell when they're wet and shrink up when they're dry. And when things heat and cool, they do expand a little bit as well, too. And all this expansion, contraction, expansion and contraction, eventually over many cycles creates pore spaces throughout the soil. What does soil look like in addition to those soil PEDs, those aggregates or clumps that we see? Well, color, of course, is an important part of soil. It helps us really to identify different layers, but it also tells us important things about the soil too. So color can indicate the amount of organic matter that is present in the soil, with really dark colors usually correlating with a high content of organic matter. It can tell us how wet or dry the soil is, the drainage class. If you see a soil that's basically all red, yellow, or brown, or some combination of those three, it usually means a dry soil that's full of oxygen. Reds and yellows and browns are usually types of iron oxide, or basically natural rust, and they form in dry soil. Where you see gray, white, or even some black splotches, That's usually a sign of a wet soil, what we call anoxic, a soil that is saturated for a good part of the year so that there is no oxygen present. When your red, yellow, and brown iron oxides are in the presence of water for a couple weeks, they actually dissolve and wash away, and what's left are gray, white, and every now and then some black splotches. So look for those splotches, and those splotches will tell you where the water table rises to throughout the year. I should mention there's one special type of soil called hydric soil. It's a really specific wet soil. Hydric soils are poorly drained soils that are mostly gray and often have a thick accumulation of organic matter at the surface. Why is it important to know what a hydric soil is? In order to be considered a wetland by legal classification, the wetland has to contain hydric soil. So a lot of times when people are out determining the extent of wetlands and what wetlands are protected and what wetlands can be built upon, they're looking to see how much hydric soil is present there. And if there is not hydric soil, there isn't a wetland. If there is hydric soil, there can be a wetland. This is a picture of what we call a katina, which isn't a word that you'll need to know, but it's basically a drainage pattern of the soil. These are real soil cores taken from a hillside in Maryland as you go from the top of the hill, down the middle, and down to the bottom of the hill. And you can see, it's hard to see sometimes on a computer screen, but hopefully you'll be able to see that some of the changes as we go from top to bottom, some of the physical changes that you can see with the naked eye, color changes. So one of the changes I see as we go from the top to the bottom is that the A horizon, the thickness of dark organic material at the top, gets bigger and bigger as we go from top to bottom. And this is often what you'll see as we go from a dry soil to a wet soil. Things break down slower in really, really wet, saturated environments. So organic matter can accumulate in that wet soil, whereas at the top of the hill in that dry soil, that organic matter breaks down very quickly and the A horizon never gets very thick. Down there at the bottom at the wetland, there is decomposition occurring, but it's very slow because there's very little oxygen in the soil to power those bacteria and funky microbes. So organic matter tends to accumulate in this soil. So that thick A horizon with lots of dark organic humus in it is a sign of a really wet soil. Another change that you'll see, and this is even a little more subtle, unfortunately, on the computer screen, is that the soil gets grayer and lighter in color as we go down. And again, those gray splotches are indicators of wetness. A dry soil will be red, yellow, and orange. A wet soil will start seeing some gray splotches, and the wetter it is, the more gray splotches you'll find. I think this next color will give you a little bit better indicator. This is a really wet soil. Generally, the soil that's wet is not entirely gray, but you can see a big splotch of gray in the middle, and also some reds and yellows kind of mixed in. This is what we call a mottled soil. But if you're seeing this type of mottled soil, those really clear gray colors with those nice bright reds and yellows and oranges mixed in with them, that's a soil that's pretty wet. Those gray colors are indicators that the water table is at this depth for a good portion of the year. This soil is probably saturated for several months out of the year, totally filled with water. So look for those grays, and those will be your indicators of where the water table rises up to. By contrast, here's a dry soil. You look through it, you see it's pretty much all straight reddish here, and over here it's more of a yellowish, but we're not seeing those gray splotches mixed in with those reds and yellows and oranges. It's pretty solid red, yellow, orange, and that's a good indicator that the soil is dry. When you're trying to figure it out, and probably there will be a question about this on one level of the test, look around you as well too. If you're up at the top of the hill, chances are soil is going to be dry. If you can see a creek nearby, if you're down in a valley and you think you see some of those gray splotches are probably indicators of wetness, because again, the lower you are in the landscape, the better the chances that soil is going to be wet. The higher you are in the landscape, the closer you are to the summit of a hill, or even on a really steep slope, but well above any valleys or floodplains, soil is probably going to be pretty dry. So some of it is just kind of using your common sense and looking around at the landscape. Here is an organic soil. This is a peat bog. We wouldn't have this in the US. This is probably from Scotland. But a soil that has a lot of organic material in it is going to have this really dark color. So, what does healthy soil look like? How do you know if you've got good soil or bad soil? Soil that can support plant growth or soil that can't? Well, it would be nice to have a good texture. And usually what we think of a good texture is a mixture of sand, silt, and clay, or what we would call a loam. Fortunately, if you have a really clayey soil, if you have a really sandy soil, if you don't have this mix of all three, there's not much you can do about it. You're sort of stuck with what you got. You want to have good structure, though. What does good structure mean? Well, you want to have kind of tightly aggregated little clumps, PEDs, that are strong enough that you have a big rainstorm and water is passing through the soil. They don't just disintegrate, they don't dissolve. And you want to have lots of big pores in between those PEDs, because those pores are the passageways for oxygen and water to get down into the soil and to the roots. And you want to have lots of organic matter, because organic matter, as it breaks down, is the source of nutrients to the soil. But organic matter also helps you create good structure, because again, organic matter is one of those things that helps to bind the soil. It's one of those aggregating agents. As soil breaks down and forms humus, the humus itself is sticky, and also the microbial byproducts of that breakdown help to get that stickiness in the soil, which allows the soil to clump together. Usually good structure is going to look like this granular structure up in the A horizon, this blocky structure down in the B horizon, and it will not look like this platy structure. This is your compacted soil. That's what you want to avoid. So why do we care? Why is soil important? Well, it does a lot of things for us. Physical support is one of those things. And I'm not going to go into this in detail, but we need something to hold up our buildings. We need something for our big trees to root themselves into so they don't fall over with every gust of wind. Soil does that. Even though it's only 50% solid material, it does that pretty well. But soil really plays an important role in the water cycle, the nutrient cycle, and carbon sequestration, or we could call it the carbon cycle. And these three cycles, it's a lot of overlap between them. I'll get into each one. So for the water cycle, and this relates well to our special topic this year of local water management and control and drinking water quality. You can think of soil as being like a global sponge and filter that covers the entire world. So no matter where you are, if you're down in a city, if you're in some of the surrounding suburbs, or if you're out in the countryside, in the agricultural land, or even up in the mountains in the wilderness, water can do one of three things when it hits the surface. It can either soak into the ground, run off the surface, or it can evaporate back into the atmosphere. And that's very important because that determines where the water goes, but also where potential pollutants go as well too. Let's get into that. So again, water hits the surface. It can be surface runoff. It can soak down into the soil, or it can evaporate or transpirate, which basically means evaporating through plants back up into the atmosphere. From an environmental perspective, ideally, we want to minimize the amount that runs off the surface and maximize the amount that soaks into the ground. Why? Because soil is a sponge and it's a filter. As water runs over the surface, whether you're in an agriculture area or an urban area, there's the potential to pick up pollutants. Anything on the surface, whether it's nitrates from the fertilizer on a farm or in your backyard. Phosphates, another addition to fertilizer. Bacteria, which could be natural in source. It could come from wildlife excrement. It could come from livestock. Oil or gas, especially near roadways. Manures. And ammonia. Ammonia is another thing that you can find both in manure and in fertilizers. It's an important nutrient, but it can be quite harmful if it gets into water. All these things are potential pollutants, both in some cases in the soil, but really in water. These are all potential water pollutants. But luckily within soil, we have clay, we have humus, and we have microbes. And the odd thing that happens is as you run water through dirt, it actually comes out cleaner on the bottom. So a lot of these things that are potential pollutants are actually attracted to the surfaces of clay, humus, and microbes. And the microbes themselves are very, very hungry and very aggressive. They protect their turf really well. So if they find, let's say, some bad bacteria like E. coli or some other stuff that you don't want to have, chances are the good microbes in soil are going to kill them off. They're going to outcompete them and destroy them so that by the time the water passes through, all those bad bacteria are killed off or greatly reduced. Even things like oil and gas, which would be a pollutant in soil, as long as it's not there in such a high concentration that it kills off all of our microbes, the microbes will be able to slowly break down that oil and gas and turn it into something much less dangerous. Now, things like nitrates and phosphates and manures, if they stay in the soil, those are actually pretty good because that's fertilizer. Plants can use that. They can take that up. The microbes can use that as well too. They can take up those fertilizers and those nutrients. So as the water passes through, it comes out a lot cleaner. And that's because, again, a lot of these things stick to the surfaces of clay and humus where they're retained in the soil, and then they're attacked by the microbes, and the microbes break them down into much less dangerous forms. So really, if you want clean water, you've got to have good soil. You've got to have that water passing through the soil in order to clean both the water that gets down to the groundwater and the water that flows out to our streams and rivers, because shallow groundwater is actually kind of the base flow source for our local streams and rivers. Let's look at the nutrient cycle now. It is a cycle, but I think sort of the most important spoke of that cycle is our decomposers. And again, this is just a general word for our bacteria, our fungi, and the microbes in the soil that break down material. Decomposers eat organic matter, and as they eat that organic matter, they're messy eaters, so they sort of spill crumbs out into the soil, crumbs full of nutrients, nitrogen, phosphorus, potassium, zinc, iron, calcium, all that good stuff. And some of those nutrients will dissolve in the soil and get taken up by plant roots. So this is a tricky thing. Plant roots only take up two things from the soil: water and oxygen. They don't take up soil particles. They don't even directly take up nutrients. What they do is they take up water and oxygen. It's the decomposers that break down organic matter and other stuff that contains nutrients, and thus puts those nutrients into a form where it can be dissolved in the water in the soil. When those nutrients are dissolved in the water, then the plants can take them up through their roots. So they're taking up this nutrient-rich water from the soil that's created by the decomposers, and those nitrogen, phosphorus, zinc, calcium, iron molecules that are within that water help the plant grow, put on new leaves, new shoots, new roots, new fruits, all sorts of stuff.
Dan, I just wanted to let you know we have a little less than 5 minutes left. So guys, if you have any questions, please put them in the chat and we'll get to them when he's done with his presentation.
Excellent, thanks. As those plants grow, it looks pretty tasty to some of our lower level consumers, whether it's a white-tailed deer, whether it's the friendly rabbit in your backyard. They eat that material, that new growth on the plants, and those nutrients that are originally from the soil created by the decomposers get passed up the food chain. It gets passed up to the predators that eat the lower level consumers, the herbivores. And of course, unfortunately, all good things come to an end. Everything does have to die at some point. So all the bodies of these critters, whether it's the plant, whether it's the herbivore that ate the plant or the predator that ate the herbivore, eventually gets returned to the soil. And all of the nutrients that are tied up in their bodies now also get returned to the soil, where the decomposers start breaking down those dead animals or their manures and starting the cycle again, recycling those nutrients so they can go back into the soil, back into the plants. That's the nutrient cycle in a nutshell. Now, clay and humus both have a really important role in both the water and nutrient cycle. So remember, humus in clay is sticky. It's attractive to materials. The materials stick to the surface of them. And the reason this happens is that it sounds odd, but clay and humus actually have a little bit of an electrical charge. From basic chemistry, positive charges are attracted to negative, and negative charges are attracted to positive. And a lot of the important nutrients in soil have a positive charge. They're called cations: calcium, magnesium, potassium, iron, zinc. All these are cations. So these positively charged ions of nutrients floating around in the soil would just wash out if there was nothing holding them in the soil. Every time we have a big rainstorm, they'd all leach out down into the groundwater, which we don't want to have happen. Instead, they stick, not permanently, but stick temporarily to the surfaces of humus and clay. And that allows them to stay in the soil so that the microbes and the plant roots have access to them. So, maybe we're talking about calcium, maybe we're talking about a positively charged ion of iron, or maybe magnesium, or even water. Water, it does not have a charge, but it's polar. It has sort of a positive end and a negative end, so it too can stick to humus and clay. I'm going to go a little faster because I know we're running short on time. Soil is a great carbon sink as well too, meaning globally it takes in more organic carbon than it puts out. But especially in our northern areas, up in northern Canada, Alaska, Scandinavia and northern Russia. This is where you find a tremendous amount of soil organic matter building up in the soils. And that's because it's so cold there that the breakdown is very, 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 very slow of organic matter. Now, the issue with this is that if you look at global warming, the areas of the globe that are warming the fastest are actually those far north areas. And if these soils with a tremendous amount of stored organic carbon start to warm, that carbon will start to break down. There'll be more microbes, more active bacteria and fungi in those soils, breaking down that organic material. And when organic material breaks down in the soil, about half of it becomes carbon dioxide. So all this organic carbon that's been stored up in those cold, cold areas for tens, hundreds of thousands of years could start forming carbon dioxide that gets put back into the atmosphere. And that could be a big problem. Luckily, there's a lot we can do with modern farming and modern land management to lock more carbon into the soil. Again, we're running out of time, so I'm just going to run through this. But with a soil survey, if you're looking for the soil locally, the best source of information is the soil survey. You can go to Web Soil Survey. Just Google or Bing or whatever, Web Soil Survey, and it'll take you to the USDA's National Soil Survey, where you can find maps and data tables for all the soils within your local area. And it'll tell you a lot of the traits, both physical and chemical, and also the suitabilities, what the soil is good for, what it's not good for. So here's some maps that you can find. This is a bushels per acre of pasture in an area, and color codes to show you what's good and what's not. This is depth to the water table. So those areas of lighter color are wetter, the areas blue are drier. Harming soil in many ways. Unfortunately, it doesn't look like we'll be able to get to it, but basically, we're trying to get people to recognize, especially on the farm, but even in urban areas, even if you only own a quarter acre of land, that soil health is really important. You can't just rely on fertilizers and pesticides to get your soil healthy. You have to look at increasing the amount of organic matter going into your soil, and also increasing the amount of those good bacteria, fungi, microbes, and critters in the soil. If we think of soil as an ecosystem rather than just a resource, and we feed that ecosystem and give good organic material, add lots of organic material into that ecosystem to feed all those small critters, we're going to have healthier soil. And if you have healthier soil, you need to add less fertilizer, less pesticides, maybe not even any fertilizer or pesticides, in order to get good growth. So sorry I had to rush through that last bit. You can see I had some more stuff, but we'll get to it later. One other thing to keep in mind too, soil quality and water quality are intimately intertwined. You have to have good soil in order to have clean water.